So we're going to pick up right where we left off yesterday, and that was to go through the second translation theorem. Which looks something like this. The Laplace transform of some function of t minus a times the unit step function of t minus a is equal to e to the negative as capital F of s. And we'll go ahead and prove this one too. Why not? So again, this is pretty straightforward. You just kind of start with the definition of the transform. So the Laplace transform of the function that we are interested in using the definition is the integral from 0 to infinity of e to the minus st times the function that we are transforming, dt. And now what we'll do is use the definition of the unit step function, since we know that it's 0 until a, and then 1 there on after. What we'll do is split up this improper integral into two pieces. So we'll go from 0 to a of e to the negative st f of t minus a, u of t minus a, dt, plus the integral from a to infinity of e to the minus st f of t minus a, u of t minus a. And now, what does this equal? From 0 to a, unit step function is equal to what? 0. Good. And then from a towards infinity, this is equal to 1. So then all we have is now the integral from a to infinity of e to the minus st f of t minus a. Okay. So now what we can do because we don't quite have anything that jumps out at us. I mean, obviously we don't know what this is. It's not quite the definition of the transform. So what we can do is this. If we let's introduce a new variable, v, equal t minus a. Then dv is going to equal dt. And now what this allows us to do, since currently, since t is from a to infinity, if I look at t minus a, what would this lower bound be now? 0. I mean, infinity is still going to be good. But now what this allows us to do is use the definition of the transform, because the definition is from 0 to infinity. So we can rewrite the integral now with a little change of variables here. We're going from 0 to infinity now. And then we have e to the minus s. And now let's change this t. If v is equal to t minus a, yep. Very good. And now we have f of v dv. So that was the key step, getting this integral back to being defined from 0 to infinity. And now we can factor out the constant, which is e to the minus as. So we have the integral from 0 to infinity of e to the minus sv f of v dv, which is e to the minus as. And now, what does this look like? It's the definition of the transform. Instead of t, we have v, but that's not a big deal. In the end, we're still going to get a transform in terms of s. And there it is. Bless you. Okay, so that one's a little bit more tricky, but not too bad. Maybe this one will be in an exam. Who knows? Okay, so before we go forward, let's kind of recap the two theorems that we have so far. First translation theorem was the Laplace transform of e to the at f of t is going to equal capital F of s minus a. Second translation theorem if we have f of t minus a times the unit step function at t minus a, the transform of that is equal to e to the minus as f of s. Okay, so I do just want to emphasize that there's a difference here. We go from a positive a to a negative a with the first translation theorem, right? Here we go from a negative a to a negative a. So just make a note of that, that with the second translation theorem, it is actually what it is, okay? First translation theorem, it's the opposite. We've gone ahead and proved why that's the case. Just make sure you keep that straight, okay? All right. Let's try a few examples. Let's say we want to take the transform of t minus 2 cubed times the unit step function evaluated at t minus 2. Okay, we want to have our parent function evaluated at t minus 2 if our unit step function is evaluated at t minus 2. So this is good. If it's not, we're going to have to play around with what's in here to get the same input. Okay? For now, this is not a big deal because we're set. So what's the answer here? We're translated, so it'll be e to the minus 2s. And then this is just the transform of second part of the theorem says just take the transform of the parent function, right? Which in this case is what? T cubed. So then this is e to the minus 2s. What is that? 3 factorial over s to the 4th. One more than a degree. So 6 over s to the 4 e to the minus 2s. Okay. Questions so far? Oops, wrong color. Not that it's that difficult, but it's worth mentioning. A lot of times you'll want to just take the transform of the unit step function. So we have the unit step function times, we don't have anything else there, but we can call it what? 1. So then we'll have e to the minus as, and then what's the transform of 1? 1 over s. So we treat 1 as equal to f of t minus a. Okay. Let's try this one. Find the Laplace transform of the function f of t that looks like this. So this is 2, that's a 3. It's hard to see, but okay. Let's write the function first. This is kind of what we finished with yesterday, right? So here's our functions, the piecewise graph. If I want to write out what it looks like, what would that be? Well, let's write it in compact form. Good. Starting at 2. Then we want to subtract 3 starting at 2. I'm going to add 1 starting at 3. But it's 0 everywhere else, right? So then we're good. And now what we can do is go ahead and take the transform of f of t. And now that we have it in compact form, we can just use the second translation theorem for the pieces that have the unit step function. Transform of 2 is 2 over s minus transform of 3 is 3 over s, and we have an e to the minus 2s plus, this is just transform of 1 again, so it's 1 over s times e to the negative 3s. Okay, so when we have constants, it's pretty easy to work with. It's always going to be over s, and you just have to throw in the exponential part of the term. Okay, are we kind of comfortable here with this? Unit step function notation, second translation theorem. Let's see what happens when it's not quite set up so nicely for us. Let's say we want to find the transform of sine of t times unit step function of t minus 2 pi. What is the issue right now? Right. If this is t minus 2 pi, this needs to be t minus 2 pi, right? Can we just put it in? Why? It's the same thing, right? The period of sine is 2 pi, so subtracting or shifting it over isn't going to change it. So this is a legal maneuver. Perfectly acceptable to do. Once you rewrite it, what's our transform going to be? Very good. This is our shift. Transform sine is just a over s squared plus a squared, whatever that may be. In this case, it's 1. Not a big deal. Okay. Last one, and then we'll finish the last part of the section. I think you guys are starting to pick up on this. But let's say we have 2t minus 3 times u of t minus 1. Like that, sorry. You guys probably know. If this is t minus 1, what should this be? T minus 1. So let's make it t minus 1. But we somehow have to keep this the same. Right now it's 2t minus 2, so how do I fix it? Subtract 1, and now these are technically still the same, right? So we have this times u of t minus 1. So then now it's e to the minus s from that portion. This gets treated as 2t minus 1, right? So all we're doing is the Laplace transform of 2t minus 1, even though it doesn't look like it. The parent function is 2t minus 1. So that's e to the minus s times, what's the Laplace transform of 2t? 2 over s squared minus 1 over s, and we're done. Okay? All right. First and second translation theorems are done. Last part. Is the derivative part of the transform. And let's just kind of get right into it. If we're interested in taking the derivative of a transform, using the definition, this is just d ds times the integral from 0 to infinity of e to the minus st f of t dt plus now we can, the derivative and integral order here is really interchangeable, so we're going to go ahead and take the derivative, put it in the integral, but since there's a multivariable function in here, we're going to rewrite it as partial s, since we have a function of t and s in here. The reason we can do that is because since we're integrating with respect to t, it really wouldn't make a difference. So let's go ahead and do some Calc 3. What's the partial derivative of this function in here with respect to s? What's the only thing we look for here? Good. So we got a negative. Let's pull that out. We have a t in there. I'm going to keep that after the e to the minus st. And then we still have our f of t dt. Well, this pretty much looks like the definition of the Laplace transform itself, with the exception of the fact that it's negative and there's an extra t here, right? So then what we can do is write it as, whenever we want to take the derivative of a transform, it really would be the same thing as taking the opposite of the transform of t, f of t, dt. Sorry, no dt. Which actually helps us going the other way too. So similarly, we can argue the same thing and go backwards. If I wanted to go from a function where we had this extra t, what we can do is, if we understand that the transform of f of t is f of s, then I could easily just take the derivative with respect to s to figure this out. Okay? And make it negative. Now, we'll do one more case so we can have a general rule. Let's say I had the Laplace transform of t squared times f of t dt, f of t. Then what we can do is say that this is the same as taking the transform of t times tf of t. So then what we can do is use the previous rule. Now we just have this extra t in there, so all that means that we're going to do is take the opposite of the derivative with respect to s of the transform of the function at hand, which is tf of t. And then we can do this again, right? This extra t here means we're going to have the original minus dds times another minus dds of the transform of just f of t now. So in this case, we just get the second derivative with respect to s of the transform. So one can pretty much use inductive reasoning here to get to the conclusion. If you have a t just kind of floating about this normal function that we know how to transform, one way that we could figure out the transform is to take the derivative of the transform with respect to s, make it negative. If I have a t squared, we just take the second order derivative, but now it's positive. You guys kind of see the pattern, I hope, right? We can keep doing this all day. Here's the general rule. So generally, whenever we have the transform of t to a power, f of t, this power of n, or this power of t, translates to what? Nth order derivative, good. Somehow we need to adjust the sign, right? So we need a -1. First case was negative, second was positive, so we could just do to the n, right? And then we have our f of s. So here's an example. Let's say we have the transform of t e to the minus kt. Sorry, say that louder.
No, you have to. I thought it was negative k to the kt, but
Right. Let's just kind of use this derivative technique, right? So all we're going to do is the first derivative of the Laplace transform of e to the kt. What's the transform of e to the kt? If I now take the derivative of 1 over s minus k with respect to s, becomes -1 over s minus k squared, which just gives us positive 1 over s minus k squared. Okay? I think you guys get the idea. Okay, the key is to, if you identify a function that you know how to find the transform of, and this is the thing that's kind of throwing you off, think of the derivative rule. Okay, because then all you have to do is find this transform, take its derivative however many times you need to, depending on what power of t we have. Yes? What do you do if you have something like what?
We combine like the first translation theorem and this one.
Okay, give me the problem. So if you have something like sine of,
E to the AT. Or of just the rest.
so you have an e to the at, and then,
Sine of t.
uh-huh,
Then everything times t.
and everything times t.
Yes.
Then what you would do is take, so if you're doing the transform of this, that's a good question, treat this as you normally would. Use the first translation theorem first, find the transform of that in terms of s, and then now you can take the derivative of that. Or if it was squared, twice, make it positive. Does that make sense? Okay. Anything else? Okay. That's the end of the section.